Alright, and here comes the long and boring video on final engine tuning and tricks and techniques and effects, blah blah blah. Just bear with me here, those of you that are interested. Anyway, if we break down our NASCAR 2003 engine profile into pieces, I would say we have the piston, cylinder and intake system, so to say, in our profile. Let me talk about the piston a little bit. For the piston, the first value that pops out is stroke. Piston stroke. In our example, it is 3 inches. That is how far the piston goes up and down in the cylinder. Let me skip to this slide. As you can see, the piston right here going up and down, compressing the fuel mixture. Also, the shorter the stroke, the less distance the piston has to travel at a higher RPM. So smaller stroke engines seem to rev a little higher or much higher than longer stroke engines, but they seem to lack the torque because the acting power on the piston only lasts for 3 inches versus a longer stroke would cause the pressure to act on the piston for a longer period of time while it's traveling. What else can I say? From having cylinder dimension right here, the size of our cylinder, CID, and in our example it is a 283 Chevy, we can find cylinder bore, or you could just look it up in the dimensions somewhere online. But I know for a fact that the bore value for our engine is 3875, and that's in inches. And that would pretty much be like the distance from side to side on the cylinder right here. Now, knowing the bore, we could find the radius, which is half of it, and then the most importantly, we could find the piston area, and that is what we're gonna need for our future formulas. Right here, the area of our piston, the size of a piston. Well, I mean, essentially it's gonna equal the area of your bore, pretty much right here where the piston is. Same thing. That's how much area is the pressure going to be acting upon. And then to that mosquito, spice it all up a little bit, we have the air induction system and the size of the intake valve. I'm gonna put it right here. Intake valve size. Intake valve size. I'll show you what it does. Basically, it just limits the amount of air that our engine can ingest at a certain RPM. It's a very simplified system because it doesn't have any cylinder head CFM flow, it doesn't have any intake manifold flows, it's missing a bunch of variables, and all it gives us is the intake valve size. But before all that air reaches the combustion chamber, the intake valve is the last barrier, is the last step limiting the intake flow in size. So it is kind of cool that they included this one, but I wish there was more adjustments for airflow. However, that's the only one that we have. We have the number of intake valves, like you can use 1 or 2, which will give you a little bit better breathing engine, but we have not tested any 2 intake valve engines because NASCAR simply doesn't use it, and those old school engines only use 1 intake valve per head. So far I've not included a thorough testing of the 2 intake valve per cylinder engines. Anyway, let me stop right here for a second and catch my breath. Alright, now in the second part of the video I want to talk about what happens in the cylinder. As before, I mentioned that earlier, we have indicated pressures. That's the pressure that exerted on the piston when the explosion happens, the initial power of the spark, of the bang that happens inside igniting the air fuel mixture. Then we have pumping losses, well, to get the air and fuel in the cylinder and then pump it out. And then we have friction losses, due to clearances, bearings, everything spinning and rotating. Definitely we get friction. So whatever is left after those 2 robust of Power is brake mean effective pressure, and that's the useful pressure that is actually doing the work on the crankshaft, not the pressure that just got in here from exploding the fuel inside the cylinder. Now the next thing to talk about in line would be what makes it into brake pressure. What kind of losses are we experiencing besides pumping and friction? And here we have three engine qualities: thermal efficiency, volumetric efficiency, and mechanical efficiency. It is three most basic, very simple things. Thermal efficiency is pretty much how well our engine is burning fuel. Is it a well-designed, well-tuned engine that burns a lot of fuel properly? Or is it an old clanker engine with low compression and gases blow by and not everything exploding, and we have raw gasoline coming out of the exhaust because, you know, it's not a complete combustion, blah blah blah, like one of those clunkers. So that would depend on how well the fuel burns inside the cylinder. That would be one efficiency of our engine. Then we have volumetric efficiency. Well, basically it is how well the engine can breathe at faster RPM. Basically, the faster it spins, the less time it has to ingest the necessary amount of air to produce the power needed. Basically, just like a human being, if I'm taking full breaths, that's slow enough for me to take a full breath. Or if I need to take 10 breaths at the same time, I'm gonna have to go and I can only suck so much at once. That's a good way to put it out. I can only suck so much at once. And damn, another mosquito. That my volumetric efficiency falls down with the RPM. Basically, here we go. Intake and exhaust gas restriction. And intake restriction would be our size of our intake valve right here. Then mechanical dynamics such as valve train, or pretty much what I mean is camshaft and how the valves close in and out, and if the valve springs are starting to float at higher RPMs. Bunch of factors are limiting the way your engine is breathing, or, you know, taking those inhales of intake strokes with the air-fuel mixture. And finally we have mechanical efficiency. Is it a well-made, well-surfaced, nice clearances, nice surfaces, everything engine, or is it an old engine with a little bit of oil in it and dirty oil and you know, crappy stuff that, you know, is not that well mechanically maintained? Basically 1, 2, and 3 different things that happened in between here to here. In between indicated and brake, we have thermal efficiency, volumetric efficiency, and mechanical efficiency. Now I need to talk about torque curves a little bit in the next segment and show you where on the torque curve we have the indicated horsepower and where on the torque curve we have brake horsepower, and how much is getting lost due to all the volumetric, thermal, and mechanical efficiency of whatever engine that we are inputting. It will become more clear with the next segment. Stay tuned. In this third segment, I must show you guys the torque curve for a LS9 engine. Just because it's a good looking curve and it is easy to explain. It could be any engine, truly. Basically, here in blue we have the torque curve, and in red we have the horsepower curve. Advertised right here to the left. Torque and power at the flywheel. So assuming if that is true and they're not lying, the horsepower rating that we have right here should actually be brake horsepower rating in BMEP, if that is truly the horsepower at the flywheel and not inside the cylinder. From here we can make the conclusion that this torque curve and these values, after they've been calculated to the BMEP, do not need adjustment, as this horsepower value is already in the BMEP. Assuming for most regular engines and torque curves that you see is going to have the I indicated horsepower rating. Anyway, the theory goes like this, as far as I know. At the maximum torque at 3800 RPM, and that would be the point right here, you could see how our engine is making the maximum power. It's breathing the most efficiently. The fuel, air fuel mixture is the most efficient. The combustion is the most complete. Basically, this is the sweet spot for the engine, is right here. This is where it's the most efficient. It burns least fuel for the power that it's making. It's right here. However, we could spin it farther at the exchange of torque loss, because we need to spin the engine faster. That means moving the pistons faster. That means more heat, more friction, more resistance losses, less volumetric efficiency, because the engine doesn't have enough time to breathe as much air as it needs to. So as you can see, we have our fall off right here. Basically, if we're going to quiet cat, I have my cat with me, I'm teaching him stuff about cars as well. If we're gonna go and take the point of maximum horsepower, and right here we already have a blue square, and translate it into the maximum torque that we have right here, yes, we could see how this top triangle that I'm gonna mark right here, basically the fall off of our torque, instead if it would be going straight forward, this is how much power, how much torque right here. This triangle on the top is how much we are losing to friction, thermal efficiency, volumetric efficiency, and mechanical efficiency, basically right here. And this is the previous slide that I was talking about, how much is going to get lost to all these bad guys right here. We could see on the torque curve as the top triangle right here. It's still good enough loss for us to increase the horsepower pretty dramatically, as you can see, because of the RPM increase. But eventually with the torque fall off, let me just estimate it, like it's gonna fall off. Eventually the horsepower is going to fall off as well. However, in NASCAR 2003, all we have is the torque curve. We don't have the horsepower curve. And on that torque curve, we have 0.1, oops, forgive me, 0.2, and 0.3 on the torque curve right here. And the 0.3 depends on how much horsepower you're making, right? And judging by this estimation, we have this triangle of how much energy gets lost to get the engine going faster. Now, my theory is that NASCAR 2003 estimates volumetric efficiency, thermal efficiency, maybe the thermal efficiency, or some of it might be pre-programmed and hard-coded and could not be changed, or some of it might be self-estimated, like the bore values, you know, volumetric efficiency, camshaft profile, you know, stuff like that could be determined by the RPM and the power value number from these 3 points, 1, 2, and 3. Depending on what kind of engine and what kind of dimensions the engine has, how much power it's making at what RPM, I believe NASCAR 2003 can estimate the rest of the needed values to calculate engine's torque curve performance, such as volumetric efficiency, mechanical efficiency, camshaft profile. I believe it's all kind of like a reverse process, so to say. In the fourth segment or in the next video, I'll show you what actually happens in game when you tune the torque curves. But for now, I think this was the long, boring video for anybody that might have been interested. Basically, we have 0.1, 0.2, and 0.3. And the fourth thing I want to mention is the difference between 0.2 and 0.3, the fall off. Dictates of how efficient, how sleek, how well breathing, how well everything our engine is to the NASCAR 2003 software game engine. Anyway, I'm gonna stop right here to fit in the 15 minutes. I'll see you guys in the next one.